So good morning or good afternoon, depending on where you are. So let me share my screen. Okay, there we are. So first, I'm just going to introduce all the different people. So Rico already mentioned everybody. So first, my name is Cormac Toher. I'm an assistant research professor at the Center for Autonomous Materials Design at Duke University. Then Corey Ozis, David Hicks, and Marco Esters here are all postdoctoral associates at the Center for Autonomous Materials Design. Rico Friedrich was a postdoctoral associate with us, and now he's at the Helmholtz Zentrum Dresden-Rossendorf. Andrew Smoljanyuk is also a postdoctoral associate with us, and then Professor Stefano Curtarolo is the director of our center at Duke University, and he will be giving the keynote lecture after this introduction. Okay, so before we start, I'm just going to go through some logistical issues. So I think everybody is reasonably familiar with Zoom at this point, but just to recap, the important points. First, please keep your microphone muted if you're not speaking. So if you do have a question, what you should do is either use the chat function or use the raise hand function. So the raise hand function is now inside this reactions button. So if you press on this reactions button, you'll get this option to raise your hand. So if you do this, then somebody will see that you have your hand raised like so, and then we can unmute you and you can ask your question, or we can send you a chat message. Okay, so next up, exercises are going to be part of each session. So for these exercises, in many cases, we will be splitting the group into different breakout rooms. So you'll get an invitation to a different breakout room, and then there'll be one instructor inside each breakout room. So you can ask this instructor for assistance, you can share the screen with them, etc. if you're having specific problems. So for these exercises, so several of these exercises will be using this TU Dresden, this VNC portal. So you should have gotten this an email about this already from Florian Pump. But so you will need to install and run this TU Dresden VPN, so this virtual private network. So if you go to this link here, it should also be in the email, and follow the instructions specific to your operating system. So whether it's a Mac, Linux, or Windows, you have different things you need to do. So once you've managed to connect to your VPN, then you need to log into the virtual machine. Again, this will be a link in the email that was sent. So a few important things to note about this virtual machine. First, please do not use this logout function, as this will shut down the virtual machine for everybody. Okay, so don't shut down the virtual machine either. If you want to exit the virtual machine, just close the browser window or the tab that you're using. And please also do not change the resolution in your desktop environment. I'll now explain how to change the actual, you need to resize the screen. Okay, so when you click on the link for the virtual machine, you'll get this connect button. So you'll get a browser window that looks like this. If you press the connect button to connect to the virtual machine, you'll get a password. So the password that was sent to you in the email is the password you should use for this virtual machine. So then once you log in, you'll get a screen like this. So then there's a few important things to note that will be important for the exercises. First is if you want to resize the screen, or if you want to copy and paste in and out of the virtual machine, you need to use this clipboard or these instructions. So if you go to here to the arrow on the left-hand side of the screen, click this little tab, then you'll get an option like this. If you go down here, you get the clipboard, and this you can use for copying and pasting things in and out of the portal. So it's a bit tricky, but because you can't copy and paste something directly into the portal, you need to use this clipboard. If you want to resize the screen, so what you should do is you should go down here to settings. Then you should select this clip to window scaling mode box, and then click here, select remote resizing. That'll allow you, if you resize the screen, then this virtual machine inside this window will automatically resize as well. Then the terminal is here, so we'll be using the command line for a lot of the exercises. So if you want to open that up, and then the other thing to note is the home directory here. So if you want to look inside, this is where some of the exercise materials will be for each day. So before we go any further, I'll just show you myself, my own virtual machine, where things are, and do some examples. So here's the virtual machine I've started. Let me hide this a little bit. So you can open and close, toggle this thing, this menu by clicking on this tab. So here's the one for the clipboard. So if I want to copy and paste something, what I need to do is, okay, if I go here, if I want to copy this file, so I can copy this. Then I go to my clipboard. I paste here like this. And then from this clipboard, I can open up here in the, so here I can open up a terminal. Show you again. So you click on the terminal. I can then run text editor like Gedit, and hopefully I can copy and paste this in here into Gedit. Maybe step that. Let's try VI instead. Okay, paste. Okay, so now we can copy and paste something into a file inside the terminal. That way, it's a bit trickier than should be, but this is one of the downsides of using these virtual machines. But it's the easiest way to do this otherwise. Okay, and then just to show you the home directory. So if you go inside home, you go here, first one you'll see is AFLOW exercises. Then you'll see day 1. Then you'll see, so we have the slides here for today, for this current lecture here. So here's the PDF copy of the slides. And then for the next exercise, the next session on, so the introduction to AFLOW, if you go inside here, you'll see the different exercise materials. And the different instructors will go through each exercise, but this is where you can find them. Okay. Okay, so now that the logistics are out of the way, we can start with discussing why we actually want to do computational materials design. So in practice, the first thing we're interested in is novel materials for specific engineering applications. So we're interested in things like thermal barrier coatings, for things like inside the turbine blades, inside jet engines, or inside gas turbines for electricity generation. We want to do wear resistance coatings for things like drill bits and cutting tools. Biocompatible corrosion resistant alloys for things like medical implants. Then something else that other people work on is things like photovoltaic materials for solar energy harvesting, or solid state electrolytes for lithium ion batteries, or solid state electrolytes are also anodes, new anodes or cathodes that improve the energy density and the cycling ability. And then finally, something that people have looked at and we've done a little bit of work on ourselves are things like superconductors, or for example, heat sinks for advanced electronics. So to give you an idea of the scale of this problem, here, if we look at the periodic table, we have about 78 elements that are non-noble gases and are more or less have stable isotopes. So if we want to look at a number of ways we can combine these elements, so this is not accounting for the different possible stoichiometries or different structures. This is just purely numbers of just pairs of elements is about 3,000. Triplets of elements is about 76,000. By the time we look at quaternary material systems, we're over 1 million. 5 component systems, you have 20 million. And by the time you get to 6 component systems, it's 250 million. Then once we take into account all the different possible structures and stoichiometries, we get up to something like 10 to the power of 177 possible hypothetical materials that we could generate. So now we have to figure out, okay, which one of those are actually going to be interesting for different applications, which ones we actually want to which ones we think could be synthesizable, which ones we think could have interesting properties. Obviously, you can't go through all of these different possible materials by hand. So instead, we do what's called automated computational materials discovery. So when we do it, we start from two different starting points. One is from experimental structures, so things that have already been reported experimentally, and for example, in things in databases like the ICSD, or we use what are called structural prototypes. And this is really for when we're trying to find new materials that haven't been reported already. And Dr. David Hicks was going to talk about these structural prototypes in detail in a session, I think tomorrow. So we start from this, we decorate these different structural prototypes with different elements to get new hypothetical materials. We then perform automated quantum mechanics calculations using AFLOW and the VASP DFT code. And Dr. Coriosis and David Hicks will also be talking about this in the sessions later today. We pipe the results into a searchable and sortable database. And then we interrogate this database either to find new candidate materials for new applications, or we use the data that's inside to do things like training machine learning models to then further accelerate this process. So the way AFLOW works is it wraps around the DFT code. You have a single input file, so this is called the AFLOW.in input file, and we'll be talking about the structure of this file in later sessions. This will then start multiple density functional theory calculations. If you have an error, it monitors the calculation. If it reads an error in the output file, it changes the input file parameters that restarts the calculation and trying to get it to run successfully. Then it runs different, once the calculations are finished, it then extracts data. So from a single calculation, it can pull out things like the electronic density of states or the band structure, or analyze the band structure to get the electronic band gap. It can also combine multiple DFT calculations to get things like thermodynamic properties, thermal properties, elastic properties, etc. And in later sessions, later on in the week, we'll be talking about how each of this processing is done. And finally, it takes the results, it formats them, and it pipes them into a database for online storage and dissemination. So in our case, our database is at aflow.org. So here's the aflow.org web portal. So here you see, if you go to aflow.org, you'll see this page. We now have about 3.5 million entries, materials entries, and about 700 million total properties. So this is like individual values that have been calculated for the different materials. Here's a breakdown of the properties, so you get an idea of how many band structures, elastic properties, thermal properties, etc. Here we have, and then we also have our AFLOW schools, like this school, for example, and also our AFLOW seminar series. So just to show this, there's some mention about the seminar series. So if you go to this seminars and schools and seminars page, first of all, you can see about upcoming future schools. So if you want to go to attend another school in the future, you can keep an eye on this page. And if you can also watch for upcoming seminars. So these typically take place on Thursday afternoon at 3 p.m. Eastern time. The next seminar will be on Thursday of next week, so September 16th at 3 p.m. Eastern time with Dr. Michael Gao. And again, you can, if you monitor this page, aflow.org/seminars, you'll be able to see when the next seminar is, and you can sign up for it, and then you'll get an email with a link to the seminar. Okay, if you scroll down further on this front page, you'll see this apps and docs menu. So we have various applications that we'll be going through, that we'll be discussing during the different sessions this week. But the first one I'm going to mention now is this advanced search, or Mendelib search as we call it. So if you click on this search option, this will bring you to this search page. Okay, so if we go to once you end up on this search page, you'll see a number of different things. So you'll see a periodic table of the elements where you can select different combinations of elements to search for. You can also select groups of elements. So for example, you could, if you want to look, if you're interested in alkali halides, you could select alkali metals and halogens. You can also specify the number of species. And this is quite important because if you were to specify alkali metals and let's say if you were to specify sodium and chlorine, you get sodium chloride, but you'd also get other things like potassium, sodium chloride, and so on. Whereas if you specifically want just sodium chloride, you specify the number of species as being 2. So then if you wanted to search for, say, alkali halides specifically, you'd also specify alkali metals, halogens, and number of species as being 2. We can also perform logic operations. So the default operation is usually an AND, but you can do things like not, or, exclusive or. You can also group different specify the hierarchy of the operations using these parentheses. Then you can also search, the default is to search only the ICSD part of AFLOW. So these are existing materials, but you also have the option to search for all AFLOW. So this includes things like, these include like the hypothetical materials that are generated from the prototypes. We can also either slide to the property filters, or you can toggle so that the property filters are all on the same search page. So if we display that, you can see it looks something like this. So now, as well as having the periodic table, you have also this option with property filters. So you can search for things like, say, the electronic band gap. So you can filter by band gaps in a certain size. You can also search for things like mechanical properties if you're interested in, say, the bulk modulus, and so on. And also the space group and the Pearson symbol, so some structural information is always displayed by default. So here, for example, if we select electronic band gap, this now comes up down here, so displays column. We want to restrict, okay, so here we select specific elements. In this case, we're doing sodium and chlorine. We set number of species 2. Then we select add to add this filter. And then we added the filter for the electronic band gap. And then we can check this box if we want to restrict the values, so we can give a specified specific value range. Okay, so let me just do a quick demonstration of how to do this. So if we go to the web page, and here we have aflow.org. So then if I scroll down, I'll find this Mendelib search. And here then, say I wanted to select sodium. So I click on sodium and I click on chlorine. And then I wanted to bring up the box at the bottom. So if I click on this display button, you'll see also these property filters. I set the number of species to 2. Then I hit electronic band gap. And let's say I want to restrict, first I'm going to not restrict the value. So I'm not going to put any boundary on it. So I'm just going to hit the search button to see what I get. So it takes a couple of minutes, a few seconds, and here we come up sodium chloride. So here you can see it displays the electronic band gap with some, and here we see the different structures. So here we see that the 225 space group. So this is the rock salt structure, so the standard structure for sodium chloride. But then we also see that we have some other structures, like here we have the simple cubic here, cesium chloride type structure, which you can also see as a different band gap. We can also put in a restriction. So let's say we restrict the value from 5 electron volts to, let's say, 6 electron volts. So this will only return ones with between 5 and 6 electron volts. Then I hit search again, and then it runs a new search. And this time there's a further restriction, so we get fewer entries. And now all of these are the rock salt structure. So it basically eliminates the other structure that a band gap of 4 electron volts. Okay. So if we go back to our page, so what we're going to do now is we're going to do a quick session, a quick exercise, just to get a little practice warm-up exercise. So this is only going to use your browser. So you don't need to worry yet about getting the VPN working. There's a question in the chat. So first, for these exercises, we will break up into our breakout rooms so that everybody can get a chance to feel how those work as well. So there's 2 exercises. First is to use the advanced search functionality to find the band gap for silicon carbide in this zinc blend structure, so space group number 216. And the second one is to use the advanced search functionality to find materials containing tin, but not lead, with band gaps between 1 and 3 electron volts in the ICSD catalog of the AFLOW database. So how many results are returned? Okay. So, and the other thing is, just in case people are having problems accessing the aflow.org server, because sometimes if this server gets overloaded, there's also an alternative server that's available at aflowlib.duke.edu. So if we want to start breaking up into our breakout rooms, so if somebody wants to start activating the breakout rooms, and okay, so we have a question in the chat. Does AFLOW work with Quantum Espresso also, apart from PowFlow and VAST? Okay, so this will be discussed a bit more in later lectures. In terms of actually running the code, monitoring and correcting the errors, AFLOW really only works with VAST. That's because the error correction, developing all the error correction software is quite intensive. It's a lot of work. And so far, it's really only been done so far for VAST. Now, there is some work you can do for Quantum Espresso. For example, you can generate input files. So there are some options to do that. And I think it might be discussed in some later lectures. But it doesn't do the full, both error management as well as data post-processing, because for each different DFT software, these error messages and the output files, the output format are all quite specific to that code. So you have to you have to develop new modules for each different code, and that's not something we've done yet. Okay, with that, it looks like pretty much everyone is back. So we can continue with the exercises. So let me share the screen. Share. Okay, so here we have the 2 exercises, and now I'm just going to run through them quite quickly before we wrap up and move on to the next session. So the first one is to find the band gap for silicon carbide in the zinc blende structure. So we have silicon. So let me clear this. So first, let me reset the search. So here we go, silicon, carbon, number of species is 2. And I want to know the electronic band gap. So I don't necessarily need to do any restriction on the value, because I can just look for the one with the appropriate space group. So here it does the search. So now I'm looking for 216. So here it is down here. And you can see there's a group of them here, and there's about 1.37 electron volts. So then the next one was to look for things with tin, but not lead. So tin, not lead. We don't want to do any restriction on the species. I want a band gap between 1 and 3 electron volts. So here I do restrict value, 1, 3. Search. Oops. So this is searching all AFLOW. So let me stop this search. So I want tin, not lead. I want the ICSD only. And I want between restricted electronic band gap between 1 and 3 electron volts. Okay, so here we find that if we look over on the right, just above the column, but this case is finding 389 entries. It should really be 369, but might be bringing in entries from outside the ICSD. So let me try again. ICSD, not lead. And then okay, now it's getting the right number. Now it's 369 entries. Okay. Okay, so now that we have all this kind of data, what kind of things can we do with it? So first thing we do is we do what's called stability screening. So this is where we try to find which materials are actually stable or which materials are actually likely to form. For this, we do this convex hull phase diagram analysis, and Dr. Coriosis will be talking about this, I believe, on Wednesday in more detail. So you can also then do things like calculating the phonon dispersion for different materials. So here, for example, the one on the left is for titanium. This is hexagonal. You can see that this doesn't have any imaginary frequencies. On the right, you can see here's the BCC titanium. So this is at 0 Kelvin. So this is the stable phase for titanium at 0 Kelvin is the hexagonal phase. So here you can see this BCC phase is not stable. This is the high temperature phase. And you can see that it has these imaginary frequencies as represented by these negative values here. And this, Dr. Marco Westers will be talking about this as well later in the week, how you can actually do these types of phonon calculations with AFLOW. And you can use this to determine material stability, but you can also look at other kinds of thermal properties as well. Then we can do things like materials design and find new design rules. So for example, here's for superconductors. So here's some work we did earlier on superconducting critical temperature. So you can see depending on which element you place here. So if you place lead, the critical temperature goes up. Whereas if you place neodymium, the critical temperature goes down. You can also find rules for things like thermal conductivity and perovskites. So in this case, in the case of fluoride perovskites, the thermal conductivity depends on the atom that's on the B site, whereas in these oxide perovskites, it depends on the atom that's on the A site. And again, you can find more details in this publication here. We can also train machine learning models to predict the values of properties, so things like thermal properties, mechanical properties, and so on. And I'll be talking about this in more detail again in a session on Thursday. So for AFLOW installation, in this case, we will not need to install AFLOW for this exercise because it's already been installed on the virtual machine. But if you are interested in installing AFLOW on your own machine, you can install it straight up on Linux or Mac. For Windows, you might need some additional software, such as either a Windows subsystem or Cygwin. And for more details on how to install and how to download the code, go to aflow.org/install-aflow. So then just a summary of what's coming up. So the next talk will be a keynote address by Professor Stefano Curtarolo. So to mix or not to mix, synthesizability, entropy descriptors, and the controversial role of vibrations and stability of high entropy ceramics. So this is some work that's been done by our group using the AFLOW code, and just it gives you a demonstration of what can actually be done and the kind of research direction we're interested in. Then afterwards, so the sessions for the rest of the day will be with Dr. Coriosis and Dr. David Hicks, which will be on DFT plus AFLOW, so how to set up fast paper files, how to run calculations, etc., how to manage the calculations. Then tomorrow, Dr. David Hicks will be talking about both about symmetry, so this AFLOW sim method, and about structural typing, so how you can use these structural prototypes to create new materials, new input files for your calculations. Then on day 3, so on Wednesday, first Dr. Coriosis will be talking about thermodynamic stability, so this AFLOW convex hull algorithm. Then Dr. Rico Friedrich will be talking about the thermodynamic stability of polar materials. So this is this coordination corrected entropies. So this is an application to correct the thermodynamic stability of ionic materials. Then on last one, Dr. Coriosis will be talking about how to model disorder using AFLOW. So this is this AFLOW partial occupation module. Then on Thursday, so in the morning, I'll be talking about thermomechanical properties, particularly how to calculate elastic properties and thermal properties using this Debye model, so the Debye-Grunizer model. Then Dr. Marco Westers will be talking about the AFLOW database and the APIs, so how you can actually download this data programmatically. So a similar kind of searches that we were doing earlier using the web portal. He's going to show you how to write a script to do these searches. So you can, if you want to really do more complex searches, download data in a format that's going to be programmatically readable, machine readable formats. Then on the final session on day 4, I'm going to be talking about our machine learning API. So how you can actually, again, incorporate machine learning into your materials design workflows. Then on Friday, in the final day, so in the morning, Dr. David Hicks will talk about the AFLOW Extel Finder algorithm. So this is how you can basically take a structure, compare it to other structures, determine what the structural prototype will be, etc. And this also allows you to do structural searches of the database. So if you have a structure and you want to find if there are identical structures in our database, you can actually use the AFLOW Excel Finder algorithm to do this. You can, then the next session will be Dr. Marco Esters will talk about how to calculate phonons, to perform phonal calculations, calculate phonon dispersions, like I showed you earlier, like the examples I showed you for titanium. And then finally, Dr. Andrew Smolyanyuk will talk about the quasi-harmonic approximation. So again, this is based on this on phonon calculations, but this is at in the quasi-harmonic approximation. So now you can really model how things depend on temperature and volume and these sort of properties. Okay. So then if somebody has a question in the chat, so what is the difference between ICSD versus all AFLOW for the search? Okay, so I think Dr. Esters will go into this in a bit more detail in his discussion, but basically ICSD there's about 60,000 or so entries, and these are materials that have already been reported experimentally. So these are materials that we know exist, and for these materials, we're mostly focused on calculating properties. So things like thermal properties, elastic properties, electronic properties, and so on. Then for the all AFLOW, this includes, as well as just the ICSD, the ones we know exist, it also includes hypothetical materials that are generated by decorating these structural prototypes. So these materials are materials that we don't know if they're going to exist or not. And this is where we do the thermodynamic analysis, and we try and predict what materials will exist. We can also combine groups of materials to predict things like the formation of disordered materials, although we won't really be going into detail on that for these methods in this session, but they are stuff we've done work on in the past. So for these materials, we'll tend to be more interested in thermodynamic properties, especially formation entropies. And there's a lot more of these types of materials because we generate them by decorating. So they're basically generated combinatorially. So hopefully that answers your question. And the all AFLOW search, it basically searches for includes those types of materials. Okay. Okay, with that, I think, unless anybody has any other questions, I think we can we can wrap up with this particular session. In about 7 minutes, I think we'll have Professor Curtarolo will be giving the keynote address. So if people want to take either a 7-minute break, or unless maybe Rico wants to give some pointers. I don't know if we wanted to open up a breakout room if people are having problems accessing the virtual machine in VPN. I'll hand over to Rico now.